So next, of course, my strategy would be to completely solve the entire problem as a constraint satisfaction problem. I know it's the big hype in classic AI. However, there's a problem. Constraint satisfaction problem has nothing called as a variable which is temporal, and planning everything is time step 1 you apply this, time step 2 you apply this action, time step 3 you supply this action. So it's not a normal conversion. In order to convert it, we consider this air cargo problem dummy example, and we say what could the solution part be. So by visualizing it, do we get idea? So let's take one variable initially true at c1 comma sfo, and there are other variables written over here, some true, some false, false not written here, true written here. What do I do next? So I apply some action, let us say load something. I'm not taking a specific example, and let's say it becomes not at c1 comma sfo. I apply another action, let's say fly something. It becomes at, or it remains not at c1 comma sfo, and so on and so forth. That's one my solution part. That's not a planning tree, it's a solution part. So you see states, action applied on this state produces this state, action applies this state produces this state, and the final state, it satisfies the goal. Now it's not a CSP per se, because a variable first takes true, then takes false, then remains false. So it's not a CSP. To convert it to CSP, what I do is I suffix time on all the states and all the actions, and these becomes my variables. So for my CSP, my variables are all time suffixed literals like at 0 c1 comma sfo, at 1 c1 comma sfo. In this example, it takes a value true, then it takes a value false, then it takes a value false, and actions. So load C1 P1 SFO at the time 1, 2. In the example, it is true, it is false. So this action was applied at time step 1. This action was not applied at time 2. So first thing that I need to do is I need to list down all the literals possible, and I need to list down all the actions possible. In actions, remember, load CP comma A is not one action. The number of actions is the number of cargoes times the number of planes times the number of airports. So many actions possible. I'll list down all of them, or it's called as I will proportionalize all variables, all actions, so that I get ground literals, ground variables, and ground actions without referring to X, Y, Z, CPA. So I first proportionalize all my variables and actions, and then I suffix time over it. Now I've got variables, all the ground variables suffixed with time, and I've got values. Either of them could be true or they could be false. What is left? Constraints. And the constraints are obvious. So if I'm applying an action, its preconditions needs to be true and its effects need to be true. So any general action, let us say at C1 comma SFO, if it is, okay, so that's the variable. So any action, let us say, if load 1 is applied C1 P1 SFO, it obviously means that at time 0, whatever preconditions were there, so like at C comma A, at C1 comma SFO, at time 0 needs to be true, and similarly for all the variables. In short, we write it as if action is applied at time t, that means the preconditions of the action should be true at time t, and if action is applied at time t, that means the effects of the action need to be true at time t plus 1. So only if an action is applied, its precondition will be applicable, its effect will be applicable, or by switching on, assigning true value, switching off, assigning false value. Just the value of the true or false applied to action, you can get everything to do with which of the variables will remain true and false, and this can nullify most of the things and give in values, and that's something that constraint satisfaction problem solver would be able to solve by assigning the actions and the literals true and false values by whichever variable heuristic it uses. Maybe it could solve for time 10 first, and then it could solve for time whatever 5. Of course, it goes on to say is that the source variables are always true. So the source was, let us say, at C comma SFO. This is a fact, so this has to take a value true because it is source. Or we say source variables at time 0 are always true. Similarly, at the finish time, whatever it is, at the finish time, all the goal variables will also be true. So these are the values that you can simply specify, which literals at initial time and the final time are fixed to true or a false value. By the way, I mean, it's true if they were true at source, it's false if they were false at source. So in general, we write down a fact as source 0. If they were true in the source, they are true. And similarly, goal t, if it was specified as mandatory true in the goal, it is true. If it's mandatory false in the goal, it's false. If it's anything else, you don't specify that as a fact. Now, typically, it may appear that's all. We've got variables, we've got effects, we've got everything. So let's just solve it as a constraint satisfaction problem, and once we solve it as a constraint satisfaction problem, we should be able to get a solution. Now there's one very weird and very difficult to observe problem. So what I'll try to do is I will try to again trace out a variable after applying in an action. So again, let me write down the same part, this time a bit more formally. So my source is at C1 comma SFO, at C2 comma JFK, at P1 comma SFO, at P2 comma JFK, and I say it's all at time 0. So now I need to append time to it, and this time let me be formal. So what do I do is I apply the action load C1 P1 SFO. So what's the P condition? At C1 comma SFO, that's true. at P1 comma SFO, at P1 comma SFO is also true. So I can just apply the effects, and let me do it traditionally how I had done that previously. So let's do exactly the same thing around. So the effects are not at C comma A, not at C comma SFO C1, and the effects are in C comma P in C1 comma P P1, and everything else, it absolutely remains unchanged. So if it's, I mean, it's a first order, it's a closed world assumption. If I mention something, it's true. If I don't mention something, it's false. So here I'll actually cut that up because it's false, so it need not be mentioned, and I just add all these things up which are true from source. So at C1 comma SFO changes, so it will get deleted. At C2 comma JFK remains as it is. At P1 comma SFO remains as it is, and at P2 comma JFK remains as it is, and this is false, so it will be just deleted. Anything written is true, anything not written is false, and let me attribute time over it. So this is all at time 1. Now let's talk about constraints. There is a constraint that because of the fact that C2 was at JFK was true at time 0, this will also be true at time 1. Why? Because I did not do anything. A parcel was kept on the table. Nobody did anything. It will be kept at the table. That's a constraint. Obvious, common sense. How does AI know it? How does AI know it? Or suppose my CSP says at 1 C2 comma JFK is equal to false, while load 1 C1 P1 SFO is equal to true. Precondition validated, satisfied, effects validated, satisfied. What's the constraint? Is there any constraint that stops it? No. As per CSP, that's valid. You did not say anything about at C2 comma JFK. You just said cargo C1 is loaded into plane P1 which is at San Francisco. You didn't say anything about C2. I changed it to false. What's the problem? No precondition violation, no effect violation. You didn't say something which was there has to remain as it is because nobody acted upon it. Now the problem is, of course, I need to add constraints. How do I add constraints that if nobody does anything, then the literal does not change? And that's called as a frame problem. So I'll try to define the frame problem so that we know at least, I mean, we also know it, what is it in English language. So the frame problem, it says that I need to add a constraint that says if P was true at time t and no action affected pt, it didn't turn it from false to true, it didn't turn it from true to false, which wouldn't be applicable, then pt plus 1 should be same as pt, or no effect means do nothing, absolutely nothing. PT is same as PT plus 1 unless some action is applied to it. So I'll try to use my logic knowledge in order to write this down as a constraint. So the exact variable that we were using was at C2 comma JFK. So let me try to use in exactly the same variable at C2 comma JFK and say that can I write this thing down. Now whatever I need to write down will be true for all of them. It will absolutely be true for all of them. So let me write that constraint down. The constraint happened because of a specific action where it did not participate. So that was load C1 P1 SFO. So I say whenever load C1 P1 SFO is applied at time 1, then it implies that if at C1, okay, I just forgot the name of the variable. So it was at C2 comma JFK, where at C2 comma JFK has nothing to do with this action. It remains as it is, or what is it at time t will be exactly the same at time t plus 1. The variables are long, so I'll write it down a bit in a shorthand notation. So if an action A is applied at time t, it means the fluent at time t is exactly the same, implies and is implied by the fluent at time t plus 1, where this is what's called as a fluent. A fluent is nothing but a temporal variable which changes with time. And F is not affected by A. So adding this as a constraint completely solves the problem. So what I've written in English language is exactly the same that I've written formally, what programs would understand. So in English language, I said action A has nothing to do with F. So Ft is exactly the same as Ft plus 1. And in logic, what I write down that if At is applied, then Ft is exactly the same as Ft plus 1. If this is not applied, then of course, you know, implication, this doesn't matter. So there is no constraint, this constraint gets freed. Now the problem is I'll have to apply it for all actions, let's say A actions, and I'll have to apply it for all fluents, let's say F fluents. So fluent is at C1 comma SFO, at C2 comma SFO, at C3 comma SFO, at P1 comma C1, at P2 comma C2, and all those literals that I have. And that's a very large number. And remember, these are all constraints. So your problem has too many constraints. And if your problem probably has too many constraints, you might like to solve it in a bit of a more optimized manner. So can I reduce this number, which otherwise completely solves the problem? And the answer is yes. So I'll try to get rid of one of the multiplicative factors of this A. I'll try to get rid of it because the number of substituted actions are too many. It's not two actions, it's all the ground actions, and the fluents are also too many. The number of variables are just too many. So what I'll try to do is I'll try to get rid of at least one factor, and let's do it. So I say my improved representation so let's again look at a specific fluent F. And looking at the specific fluent, can I guess its value at time t plus 1? If I can guess its value at time t plus 1 based on its value at time t, solved. Number of fluents, that's all. No multiplication of the number of actions. So let me try to guess its values, implies and is implied by, that same in mathematically as if and only if. Now, all that I need to say is that the value at time t plus 1, same as last time, will be exactly the same as the value at time t. So something is capped, it will continue to be remained, with one exception: if something changes its value. And if something changes its value, then it will change. So I say or action with f as effect. So I say action with effect f. So if any action is applied where ft is the effect, then it will get a positive value. If any action is applied which has ft as an effect, it will get a positive value, and that's exactly what I said. So ft plus 1 retains its old value unless and until or action is applied which has ft as the effect, then it changes from negative to false. Now it turns out that there is another criterion, that it will only keep its old value if you have unless and until you apply action with effect not f at time t. So let's write it first intuitively, and then I'll come up to this formula. So let me first write it down as English language. So I'll say f will be positive, or f will be true at time t plus 1 if and only if I apply an action with f as effect at time t. So at time t, I applied an action which has f as the effect. It'll suddenly change from negative to false. Wonderful. And the second is f was true at time t. So if f was true at time t, f will remain to be true at time t plus 1. If it was false at time t, it will remain false at time t plus 1. So we're considering 2. If f was already true at time t, it will remain true at time t as long as I do not apply an action with not f as effect. So now let me rewrite it up in a logic format. So I say ft plus 1 implies and implies by condition number 1 is action with effect f at time t, or number 2 ft and this should be not action with effect not ft. So this is 1, this is 2a, this is 2 and this is 2b. So that's your 1, that's your 2, that's your 2a, and that's your 2b condition. So let's just write it down in an actual problem very quickly to see what the constraints will look like. So I just pick up any one variable out of here and I try to solve the frame problem for exactly that variable. So let's very quickly pick up a random variable So let's say my random variable is, I'm on the air cargo. So let me just take in one of the random variables here, and after taking in that random variable, I will see what is the way by which I could write that down. So let's say at oops. So let's say the random variable that I take in is at, it's right over here, c comma a at c1 comma jfk. So at c1 comma jfk will remain to be true as long as either I apply an action that has at c1 comma jfk. Now which has at c1 comma jfk? So this could be 1, but then P is a plane, it's not a cargo, bad luck. At C1 comma A, that is 1, and there's no other. So if I apply unload at time T at CPA at C1, P and A, JFK. Now remember, I am leaving it up at a general P. What you need to do is you need to repeat it with every P. The actions have to be ground. So you will say it as P1 or unload T C1 P2 JFK or unload T C P3 JFK. So either I apply any one of these actions and then suddenly at C1 comma JFK becomes true, or what I do is I say it was already true at C1 comma JFK was already true at time T. Now I just don't need to apply an action which will cause it to become false. So do I have not C1 comma JFK anywhere? Not C1 comma JFK. I think I have it here. So that's load. So I cannot apply load CPA. So I cannot apply a load CPA. So I cannot apply a load CPA. And you of course repeat it with all the variables here. So I cannot even apply load C2, C1, C, P2, JFK. I cannot even apply a load C1, P3, JFK. So in the previous example, these were my conditions. 1, all the actions that cause the variables to change from a false to true. This was my 2a, that the variable was already true at time t, and these are my variables 2b. I cannot apply any action which changes it from a true to a false at this constraint which solves the frame problem. And of course, now my now my new complexity will be, or my new number of constraints will be the number of fluents times a small k, which is the number that you have around here, which is generally smaller. So summarizing how I did end up solving or representing my problem as a constraint satisfaction problem, the first thing that I needed were definitions of what are variables. And my variables were defined as any action suffixed with time easy enough. That was the easy part of it. Then I had to specify values, of course, true and false, action applied, action not applied. This was also simple. My initial variables were given by my initial state, assumed to be true or false as specified, and my goal variables, true or false, was constraints that I obviously had it, and source and goal were obviously added as kind of unary constraints, so I know the values, I can directly inject them up. Then I had the precedence constraints added. So action at time t implies the preconditions need for the action A need to be applicable at time t. The effects now I don't need because this takes care of the effects, by the way. Once I do that, all I do is that I inject in these constraints which solve the representational, which solve the frame problem about how to specify that something, if left without doing anything, absolutely doesn't change. And once I do that, I can simply apply a constraint satisfaction problem solver. It will solve whatever order it likes, and it will give me the values of actions if they are applied or if they are not applied. Now that's the interesting part of it. Everything depends upon action is applied or action is not applied. So your actions are your actual variables. The fluents, the literals, they can be derived from these actions by this definition. So all you need to, the CSP solver needs to do is to try to find out whether the action will be true or false. Now once I do that, I have really solved my planning problem. Whichever action were true at time t, I'll apply that. Which are not true, I'll not apply that. If you want only one action being applied at any time, you can add that as a constraint to the CSP. CSP solver will satisfy that. Only one action applied at every point of time, so that you get a linear path and not a parallel path where you could do multiple actions simultaneously. And the beauty of it remains the fact that once you model the problem as a CSP, it's like the machine learning. Once you have your data, you give it to machine learning as a black box, it will learn it. Here, all you have to do is to convert the planning problem into CSP variables, constraints, values, give it to a CSP solver, and it will give you the absolute solution to it, which you can execute it up. And with this, I'll also end up the lecture. Thank you.